Welcome to this video on testing a hypothesis about a population mean. The lesson goals are, first of all, to determine the null and alternative hypotheses, then to calculate the test statistic, then calculate the p-value or find the critical values, and make a decision to reject or fail to reject the null hypothesis, h sub 0, and finally state the conclusion about the original hypothesis or claim. So first of all, some examples of hypotheses about mu, the population mean. The original claim or hypothesis could be that the mean time is 35 minutes. Then the null hypothesis would be the claim that mu is equal to 35, and the alternative hypothesis would be that the mean is not equal to 35. The null hypothesis always includes equality. The null hypothesis is always going to be that the mean is equal to some value. So if that's the original claim, then that's the null hypothesis, which is then going to be the underlying assumption for the test. In the upper right-hand corner, we see the original claim or hypothesis is that the mean time differs from 35 minutes. If the claim is that the mean is different from some value, then that's the alternative hypothesis. Again, because the null hypothesis has to be that the mean is equal to some value, in this case 35. In the lower left-hand corner, the original claim or hypothesis is that the mean time is more than 35 minutes. So this also would be the alternative hypothesis, that mu is greater than 35, because again, the null hypothesis has to be that the mean is equal to 35. The alternative hypothesis is always that the mean differs somehow from a certain value, from the assumed value in the null hypothesis, in this case that it's greater. And finally, the other type of situation would be claiming that the mean time is less than something like 35 minutes, and that's also the alternative hypothesis. In this case, HA is mu is less than 35. HO is, again, that mu is equal to 35. So if you look at these four possibilities, the null hypothesis is always that the mean is equal to some value, in this case 35. And the alternative hypothesis is that the mean somehow differs from 35. Either it's just not equal to it, or it's greater, or it's less. So which one's the claim is very important to identify for future reference for when you want to draw your conclusion about the claim. So you can see in this case when the claim is that it is a certain value, that's HO, whereas when the claim is that it's not, different, greater, or less, that's HA. Calculating the test statistic is done with a formula. There are two cases when sigma, the population standard deviation, is unknown and when sigma is known. When sigma is unknown, we need to use the t-distribution and the t-score formula. So we take the sample mean, subtract the hypothesized mean, divide that by the sample standard deviation divided by the square root of the sample size. For example, with the null hypothesis as before, that mu is equal to 35, that's the hypothesized value of the mean. So that's mu sub 0 in the formula. If the sample size n is 20 and the sample mean x bar is 29 and the sample standard deviation s is 8, you can see the t-score is calculated as 29 minus 35 all over 8 over the square root of 20, which comes to negative 3.35. In the case that sigma is known, we use the normal distribution. And we have a z-score formula that you've seen before, that we take the sample mean minus the hypothesized mean divided by sigma, the population standard deviation, divided by the square root of n. Example, when the null hypothesis is that mu is equal to 35, again 35 is the hypothesized mean, mu sub 0. If the sample size of n equals 20, the sample mean x bar is 29, and now the population standard deviation sigma, suppose, is known to be 15, we plug that in for the standard deviation to get the z-score, 29 minus 35, all over 15 divided by the square root of 20, which comes out to negative 1.79. So in that case, we are only 1.79 standard deviations to the left of the mean in the normal distribution. Then we calculate the p-value. The test statistic tells you position of your sample statistics on the sampling distribution. The p-value gives you a probability of being that extreme or more. So the p-value is the area beyond the test statistic in the direction of the test. When sigma is unknown, we use the student t distribution with n-1 degrees of freedom, where n is the sample size. And we can find these with tables or technology. For example, if the test statistic is t equals negative 3.35, as in the previous example, and the degrees of freedom is 20 minus 1 or 19, the alternative hypothesis is mu is less than 35. That would be a left-tailed test. And then the p-value is the area to the left of t equal negative 3.35, which is only 0.0017, very small probability of being that extreme. If the alternative hypothesis is that mu is greater than 35, then the p-value would be the area to the right of the test statistic, which in this case is quite large, 0.9983, the complement of 0.0017. And finally, if the alternative hypothesis is that mu is not equal to 35, that's what we call a two-tailed test. And in that case, the p-value is twice the area beyond the test statistic, in this case, 0.0034. Similarly, calculating the p-value when sigma is known, the p-value is the area beyond the test statistic in the direction of the test on the normal distribution. And again, we can find this with tables or technology. For example, if the test statistic is z equal negative 1.79, as in the previous example, and the alternative hypothesis is mu is less than 35, that's a left-tailed test, and then the p-value is 0.0368, the area to the left of z equal negative 1.79. If HA is that mu is greater than 35, that's a right-tailed test. And then the p-value is the complement, the area to the right of the test statistic, which in this case is, again, quite large, 0.9632. If HA is that mu is not equal to 35, that's a two-tailed test, and then the p-value is twice the area beyond the test statistic, which in this case is 2 times 0.0368 or 0.0736, about a 7.36% probability of being beyond that test statistic in either direction. These can all be calculated with the TI-8384 calculator. In calculating the test statistic and p-value with sigma unknown, we use a t-test, which is under the Stat Tests menu on your TI-83 or 84 calculator. So in this same example where h sub 0 is that mu is equal to 35, you put in 35 for mu sub 0. When the sample size is n equal 20, the sample mean is x bar equal 29, and the sample standard deviation s equals 8, you put those in for the corresponding symbols. Sx is the standard deviation from the sample on the calculator display. And then you select the appropriate inequality for the alternative hypothesis. So you select either not equal, less than, or greater than, depending on whether you have a two-tailed, left-tailed, or right-tailed test, so that it knows which way to calculate the p-value. And you can see in the displays, for your left-tailed test, when HA is mu is less than 35, we get the p-value of 0.001666, which rounds to 0.0017. In the right-tailed test case, when HA is mu is greater than 35, we get a p-value of 0.9983. And in the two-tailed test, when HA is mu is not equal to 35, we get a p-value of 0.0033. All of them, of course, have the same test statistic of negative 3.35. calculating the test statistic and p-value with the TI-8384 calculator when sigma is known, we use a z-test. So you go to your stats button and select the tests menu and select z-test, which is the first option, and similarly put in what is asked for on that menu that appears, mu sub 0 being 35, the population standard deviation sigma equals 15, the sample mean x bar equals 29, the sample size n equals 20, and then select the appropriate inequality for the alternate hypothesis, HA. Either mu is not equal to mu sub 0, two-tailed test, or mu is less than mu sub 0, left-tailed test, or mu is greater than mu sub 0, right-tailed test. And the displays for each situation are shown, where if HA is mu is less than 35, that's a left-tailed test. The z-score is negative 1.7888, which rounds to negative 1.79. The p-value is the probability of a z-score being less than that, which is only 3.68% probability. When HA is that mu is greater than 35, same z-score, but now the probability of being to the right of that z-score is 96%, 0.96318. And finally, in the two-tailed test case, the alternate hypothesis mu is not equal to 35, then we want to know what's the probability of getting a z-score either to the left or to the right of 1.79 standard deviations from the mean, and that one comes to a 0.0736 or a 7.36% probability. Another approach for making our decision besides the p-value is finding the critical value. The critical value is just the t-score or the z-score that cuts off a given area known as alpha. Alpha stands for your statistical significance level. So if sigma is unknown and alpha is given to be 0.05, which is the most common level of significance, you use the degrees of freedom, which in this case we're using an example of n equal 20, so the degrees of freedom for the t-distribution would be 19, and then we can use tables or technology for this given alpha and these degrees of freedom. So for your left-tailed test, the negative value is used because you're on the left of the t-distribution, and the t-score that cuts off 5% of the distribution is 1.729. Again, from tables or technology. And then the left-tailed test is the negative of that. The right-tailed test critical value is T alpha equal to the positive 1.729. And if you have a two-tailed test, then you want to find the t-score that cuts off half of alpha on either side. So you have to look in a different place in the table to see, in this case, half of 0.05 would be 0.025. So we take both positive and negative t sub alpha over 2, in this case, plus or minus 2.093. Similarly, if sigma is known, we can use the normal distribution table or technology. Again, if we're given that alpha is 0.05 for a left-tailed test, negative z alpha would be negative 1.645. For a right-tailed test, positive z alpha would be positive 1.645, and a two-tailed test, plus or minus z alpha over 2, which in this case would be 0.025 again, would be plus or minus 1.96. Then we make the decision. So here is where you look at either the p-value or the test statistic and compare the p-value to alpha or compare the test statistic to the critical value. If the test statistic is beyond the critical value, then we say it's in the rejection region, and we reject the null hypothesis and support the alternate hypothesis. This is also if the p-value is less than alpha, our significance level. That's when the probability of being beyond that test statistic is too small to believe in some sense. very significant, less than alpha. So we reject the null hypothesis. We conclude that it cannot be true. It's too unlikely. And then we support the alternative. If the p-value is greater than or equal to alpha, that would be not significant. And in that case, the test statistic would not be beyond the critical value and not in the rejection region. And so we would fail to reject the null hypothesis. It could be true. And so we'd also fail to support the alternative hypothesis. It might be false. Here's a picture showing the rejection region and the comparisons of these values. So this is a right-tailed test, and the significance level alpha here is 0.025. The p-value in this example is 0.0212. So you can see that the p-value is less than alpha. So this is significant. Notice that the p-value is the area beyond what would be the test statistic of 2.03 in this case. So the p-value is the area of the blue region. Alpha is the area beyond the dotted line, the pink and blue regions together, and that's larger. That's a larger probability, slightly larger. The cutoff for that alpha, the z-score that cuts off that area, is 1.96. That's the critical value. So we have a critical value of 1.96, cutting off an area of alpha for the rejection region. If we have a test statistic, as in this case of 2.03, that's in the rejection region. So we reject the null hypothesis. That corresponds to a p-value being smaller than alpha. If we were not in the rejection region and the p-value were bigger than alpha, everything would be to the left of that dotted line. And to the left of the dotted line is where it's not significant and we fail to reject the null hypothesis. And here's another one for alpha equal 0.01, which would be a very high significance level. You can see that the critical value for alpha equal 0.01 is higher. It's 2.33. The area, again, represented by alpha is the pink and blue regions together. The area to the right of the dotted line is the rejection region. And in this case, we have a test statistic of 2.53, which is in that rejection region, and a p-value of 0.0057, which is less than alpha. So again, in this case, we would reject the null hypothesis. And when you reject the null hypothesis, you support or accept or conclude in favor of the alternative hypothesis. So the summary is that we reject the null hypothesis and support the alternative hypothesis when the p-value is less than alpha or the test statistic is in the rejection region. For example, conclusions about hypotheses about mu when the p-value is less than alpha and the claim is the null hypothesis. There was one case from our previous 4 where the claim was the null hypothesis, and that's when the claim is that the mean is equal to some value. Our example is that the mean time for delivery of a pizza or for standing in line, mean time for some situation is 35 minutes. So the claim was the null hypothesis, mu is equal to 35. If the p-value is less than alpha, then we would reject that null hypothesis. And our conclusion then about this claim is that there is sufficient evidence to reject the claim. We would conclude basically that it's probably not true. When the conclusions are, when the claim is HA, the alternative hypothesis, those were the other 3 cases. In those cases, if the p-value is less than alpha and we're rejecting HO, we support HA. And so our conclusion would be that there is sufficient evidence to support the claim. On the other hand, when the p-value is greater than or equal to alpha, or the test statistic is not in the rejection region, then we fail to reject the null hypothesis and fail to support the alternative hypothesis. So again, let's look at the conclusions about the hypotheses about mu, in this case when the p-value is greater than or equal to alpha. If the claim is the null hypothesis, remember when the p-value is greater than or equal to alpha, we cannot reject HO. So we cannot reject the claim in this case. And we say that there is not sufficient evidence to reject the claim, because that's why we couldn't reject it, is the evidence was not extreme enough. Finally, when the conclusion involves a claim about the alternative hypothesis, again, we word it in terms of whether there is or is not sufficient evidence. And when the p-value is greater than or equal to alpha, there's not sufficient evidence. But when your claim is HA, we turn it around to say that that's to support the claim. So when your claim is that the mean somehow differs from a value, that's going to be the alternative hypothesis, and the wording of your conclusion is going to be in terms of whether you can support that or not. When the p-value is less than alpha, we would say, yes, that's sufficient evidence to support the claim. But when the p-value is greater than or equal to alpha, there's not sufficient evidence to support the claim when the claim is the alternative hypothesis. I hope you've enjoyed this video on testing hypotheses about claims, about means, and I hope you found it helpful.